Hey everyone, it's Eugene Lisho here, and welcome to Forensics Talks. Today is all about audio analysis, and this is Forensics Talks episode 111. So my guest today is Henry Vega, and we're going to get into that in just a second. Now, just so everybody knows, this is a pre-recorded video, and so sometimes we do this. We don't do too many. We normally do them live, but nonetheless, while we air this, you can still put comments in the chat window and we can comment back. But the video itself is recorded. So if you are online, go ahead and do what we usually do and type in where you're from. Type in the city or the country where you're watching from. It's always great to see where people are while they're watching this. The second thing is you can always comment, right? So if you have any questions for our guest today, please go ahead and do that. And then finally, if you like and subscribe and do that thing, that'd be fantastic. And you can always find out when there's a new episode of Forensics Talks. So let's get started on this particular episode. And I'd like to do a little brief introduction here. So today's guest is Henry Vega. Henry is a forensic engineer with JS Forensics Consulting, and he's based in Illinois. He's a licensed professional mechanical engineer, an ACTAR accredited accident reconstructionist, an FAA certified UAV pilot, and an associate member of the Audio Engineering Society. So we're going to be talking about audio today. He holds a degree in mechanical engineering from Northern Illinois University, and he's worked in failure analysis and accident reconstruction since 1998. Now, Henry brings a broad range of expertise in analyzing crashes involving commercial vehicles, motorcycles, pedestrians, and more. His research and publications in forensic audio have explored calculating vehicle speeds using dashcam audio, and he's currently collaborating with experts worldwide on projects involving tire acoustics, firearm audio from bodycams, and roadway analysis across the UK. He combines drone imagery, 3D laser scans, and advanced modeling tools like PC Crash and 3ds Max to reconstruct complex incidents with precision. And I've been fortunate to work with him on a previous project where we were looking at audio from body cameras for firearms analysis. So let me bring him in here. And there he is. Hey, Henry, how you doing?
Hey, I'm doing well. Thanks.
All right. Well, great to have you here. And we've got a little bit of a working relationship here. So just for full disclosure, people know that we kind of know each other fairly well, and we've done some work together. So yeah, I'm happy I got you on here finally. We've been talking about it for some time.
That is true.
So first thing, I want to talk or give people a sense of your background and kind of who Henry is. So I often start early on, if you go back to, when you were in school and, thinking about what you were doing, were you always headed towards the engineering field? Like, is this where you thought you would be originally, or were you on a different path?
I was certainly in a different path. It turns out that I was interested in architecture, and eventually I found myself drawn towards the math and science aspect. And I honestly thought I was going to be doing some kind of design. And as you can see, I'm not doing design. I'm actually doing forensic analysis.
Yeah. Did somebody introduce you? Did somebody motivate you into the engineering field, or how did that come about?
Actually, that is interesting. When I was interested in architecture, I realized that there were some kids in my class that were working on electrolysis. They were separating oxygen and hydrogen from water. And just the simple concept of doing that is interesting in itself. But these individuals were like in 5th grade. And I thought there's got to be more to this whole aspect that I need to look into. And ever since then, I took an interest in the science and math. And eventually I found myself moving away from this concept of designing homes to maybe working on science projects. And that's what I pursued in college.
Okay. So you ended up being, it sounds like you were sort of a technical kid. I mean, of course, architecture is creative as well. There's a creative side to, I think, architecture, but it's technical too. So, it's interesting you have sort of both of those interests. Now, when you took the mechanical engineering, did you jump into forensics right away, or was there a different area you were working in?
No, I had no idea what mechanical engineering had entailed. I just knew that it was very broad, and it offered a wide range of possibilities, from automotive to structural aspects, I guess. But when I was in college, university, when I was in the university, I realized that I didn't have any friends or family in the engineering field. So as a result of that, I decided to go off on my own and learn how to do 3D CAD, because 3D CAD at the time was new and people were switching from the board to working on actually CAD systems. So I ended up learning 3D CAD, and I went to various engineering firms when I was going through college and offered my services. As a result, I ended up working in the mechanical engineering area, civil, electrical, and I realized I could basically do any kind of engineering I wanted. And then I thought, do I really want to just do mechanical, or is there something I would like to focus on? And it wasn't until graduating college, about a month before college, that a forensic company came to our university and talked about how forensics was taking Z to A. So in other words, engineering typically goes from A to Z. You start with a process and then you work your way. But in forensics, you're starting from Z and working backwards. And the whole concept was just so fascinating that I thought, this is what I want to do. I couldn't believe there was even a job for this. I couldn't believe people were actually getting paid to put back together these pieces. And keep in mind that back then, in the 90s, the whole concept of forensics just didn't exist. Those shows weren't really popular at that time, so I didn't know what forensics meant. But once I realized, I was hooked. I needed to be part of it.
Yeah. I kind of had the same experience. I remember, and same thing as you, like I got into 3D modeling and some of that. Actually, I'm just curious, what were some of the early programs? Because I started on AutoCAD in university, and then there was like SolidWorks and Unigraphics and CATIA, and there's all these other programs. You remember what you were using?
Yes, I ended up, I was exposed to CAD, AutoCAD back in 1988. And then I was exposed to CAD Key, which was more three-dimensional. And I soaked it up so well that I ended up learning how to do Lisp, which is the programming language of AutoCAD. And I thought, maybe I want to do a little bit more than just be the drafter or work as a designer. I want to actually know how this actually comes together. Yeah,
for sure. And you started with, when did you start with JS Forensics?
In JS, 2021, I believe. Yes, 2021. I ended up starting with JS Forensics.
And before that, you had already gotten like your, for those that don't know, ACTAR is a kind of certification for like accident reconstructionists. And you were already doing some other stuff in the field, right? Yes.
Prior to coming on with JS Forensics, I had already obtained my PE license as well as the ACTAR. And I had already done crash testing and product testing. So we were burning vehicles for the research purposes, of course, doing component testing, which I ended up doing when I was down in Texas. And I had the opportunity of working with a massive pendulum where you attach a piece of componentry, whether it's a vehicle or not, and then you just subject it with a battering ram. It was, I believe, about 2 stories high. And when you're working on something like that, you needed a team of individuals to make it work smoothly. So it was interesting and it was fun.
Yeah, for sure. I guess I should give a shout out to Jeff Suey, who's I guess the J and the S in the JS Forensics, yes. and he was a past guest also on Forensics Talks, and he's also been a speaker at the Forensic Photography Symposium in the past. So he was talking a lot more, focusing on lighting and that sort of thing. So Jeff, if you're listening, thanks a lot. Appreciate it. Yeah. So let's start getting into the audio here. So what was your first sort of exposure to the whole audio, and when you were like, hey, this is a thing here, like this is something that I can do? Tell me about the introduction to audio.
Interesting. When years ago I ended up working on a case. It was an officer involved shooting, and my scope was nothing related to audio. It was to simply take an image of a body dash camera and deconvolute it, which basically means removing the blur. And then I ended up writing a program in MATLAB where I was able to remove the blur. And I noticed something that I thought was interesting. It looked like there was more to the story. And when I approached the attorney who hired me, I was surprised to find out that there was far more data available. For example, there were body cameras, 4 different body cameras with video and audio. So as a result of that, I thought, why not look at the video, but let's see what the sound has to say. And I bring this up because for the most part, individuals, when they're giving video, I'll be the first to admit it, I want to see what it has to, what it has depicted.
The visual component, you mean, right?
The visual component, but the audio is almost left to the side. And it all started with a simple fact. I asked how many bullets were discharged, and they thought, well, maybe 5 or maybe 6. And I thought, there has to be a definitive number. And there's one way to actually do that. And prior to that, I've had an interest in vibrational analysis. So I thought, take the audio and look at it in the spectrogram, where you can actually filter out the different types of frequencies. And I was truly impressed. I had never seen ballistics audio before. And you could definitively see how many discharges, but not only how many discharges, the timing. So now you had timing, and there was another component that I even found even more fascinating, which was location. Because a discharge of a firearm in a hallway versus the discharge in an open room will have a different signature, especially if they both have the same firearm and the same ammunition. And that's when I realized I could do far more if I have the audio. And if you take into account the photographs that were taken at the scene, along with the laser scans, I ended up doing trajectory. So now we have trajectory and we have sequence. And as a result of that, I decided to approach the attorney and ask to do more than just the deconvolution in that case.
Interesting. Yeah, that's pretty cool. And so that's the start. And then from there, it sort of took you on to, like, you've got a couple of papers, and we'll bring them up in a second here. But when did it go over to the automotive side or like the accident reconstruction side? How did that flip over?
You know, when I tell people this story, they told me you really should work on a better story, but it's the story that you can't change it. I was on my way to work one day, and I realized that every time I went over a roadway bridge with concrete expansion joints, I heard a thump. And when I heard that, I thought, what are the chances I can actually calculate the speed of my vehicle if I knew the timing between those two sounds? So at the time, I didn't have a dash camera. And that's when I purchased a dash camera. It was a low quality dash camera. Nevertheless, the audio was superb, because by bringing the audio in the spectrogram, I was able to see the actual frequency impulses, which were depicted in a vertical manner. The first one denoted the front axle. The second impulse denoted the rear axle. And the amount of data that you could capture was truly fascinating, because even though you had wind, the wind was on a different frequency. So when people criticized that this couldn't be done, I was under the impression they didn't have the concept that it could be evaluated in the spectrogram. Because for most people, when they think of audio, they think of a time domain, which as time progresses, you have valleys and peaks. But in the frequency domain, it's a different avenue. And at that point, I approached Jeff, and I told him I would like to do research in audio. And he said, run with it. What do you need? And he provided me everything I needed. I ended up purchasing a much better equipment than I currently had. And then I ran with it, and I realized you could. And from that point, I didn't only realize that you could do speed from the wheelbase of a vehicle if you had the timing, but you could also calculate the speed of a vehicle going over rumple strips if you take into account the beats phenomena, which I had known from this interest I had with vibrational analysis. That paper I thought was just going to end there, and it didn't, because during the research, there was a frequency that seemed to change with vehicle speed. And I spent the next couple years trying to determine how I could actually come up with a mathematical equation to model that. And eventually, the second paper, which you had mentioned, came up, and I'll go into more detail. But if you have any questions on what I've done in the first paper, please ask me.
Well, I'm going to ask you in a second here, but actually you mentioned something about, you said like you upgraded your equipment. Do you have any thoughts on, or could you maybe just give some of us a little bit of insight into the hardware and the software that you use? And this is from a testing perspective, because
Sure.
obviously when you're on the receiving end, it could be a body camera or whatever, but have you found that there's a camera or something that has really good audio and like you're surprised by it? And what about the software that you're using too?
Okay, so when I took the audio from the dash camera, I ended up getting a low quality. I shouldn't say low quality. It was a lower end dash camera, and the dash camera had sufficient audio. It was recording at 32 hertz on the audio channel, and it was enough to pick up minute details that you couldn't possibly obtain using photogrammetry methods. I then ended up obtaining GoPros to compare up against the dash camera, and then I ended up getting a high quality Rode wireless microphone. I realized that regardless of what dash camera I was using or what recording medium, audio had a tremendous amount of data, whether it was a low quality dash camera or whether it was a higher quality a GoPro. I took the audio, I separated it from the video, and then once I inserted it into Isotope, which Isotope allowed me to visualize information and not alter it in a way that one would consider spoliation. As a result of that, I was able to develop a method, which I then shared with the two individuals down in California, Justin No and
Ziad Hadab.
And I showed them, and they helped me bring it in together, and we made a really good paper on that.
So what kind of frequencies are we talking? What's the range of frequencies that you're typically picking up with these kinds of devices? And is it just because there's enough bandwidth in there that we can get the low and the high frequencies and everything in between, that you're able to separate, different frequencies out?
Yes. Well, when you're dealing with a spectrogram, what you're essentially doing is you're taking the time domain, which I had mentioned before. You have, as time progresses, you have valleys and peaks. When you do a fast Fourier transform, which is a way of taking all of the frequencies and separating them out like in bins, and then you stack them together and you have a timeline of frequencies and time. So time is on the horizontal line, and on the vertical horizon, you have the different frequencies. And the intensity coming out of that 2D image is the intensity of the amplification or the strength of the frequencies itself. The frequencies I was dealing with were between 0 and 2000. Within that range, I was able to see the difference between the wind that the vehicle was recording, which was at the lower end frequencies, and then you had the higher frequency, which is the frequency that was being created by the wheels as they were turning on the roadway. But when you're going over roadway anomalies, you'll notice that you get impulses, which is a vertical cascade of frequencies from the beginning all the way to the top. So it's like a vertical line. You know exactly where it happens when the front wheel interacts with a concrete expansion joint and the rear expansion joint. The rear wheel contacts the expansion joint. So anything between 0 and 2000 frequencies, 2000 hertz was well within what any kind of dash camera could possibly capture, and it did an amazing job. So you don't need high-end equipment to record. It got to the point where I was even using my mobile phone to take sound measurements, and I realized you really don't need high sophisticated equipment to make recordings. You just simply need a simple dash camera, and if you happen to be leaving a voicemail as you're going over the roadway, that also works, because I checked it out and it works.
Oh, that's interesting. I didn't think about leaving a voicemail. I mean, you're still recording. Yeah, it's a very good point there. Nice. Let me bring up these papers so that people can see. There's a couple papers here that we're going to be talking about. So one is from April 2023. The other one is from April 2025. So almost like 2 years apart for getting these things published. But yes. Could you go through the basically what you did on the first one, and then how that led into the second one, and kind of like overall, give a summary of your findings.
So, as I mentioned before, I was driving down the roadway, and I wondered whether or not I could actually calculate speed using the wheelbase of a vehicle if I had a recording device. That's what brought about the first paper, which was 2023-010632. That's speed determination using audio analysis of dash camera video for vehicle accident reconstruction. Back then, I ended up using a neck-based camera, and as well as GoPro cameras to try to determine audio. And I ended up using VBox to capture the ground truth speed. So when you have the ground truth speed and you have the audio, you have something to compare it up against. By doing so, I was able to determine that there was somewhere in the order of, I believe, a 3 mile plus or minus 3 mile per hour accuracy there. And this roadway was ideal because you had 9 expansion joints. So I was able to increase my speed and decrease my speed and test various locations using that same roadway. And now that roadway happens to be the go-to place for me to do testing. Would you mind scrolling down a little bit more? I then eventually realized that if it worked for a neck space, I was wondering if it worked for other types of dash cameras. So I reached out to Justin No out in California and asked him to conduct testing over rumple strips. He found a rumple strip area, and he drove over it at a known speed, being recorded by a VBox. And then we applied this whole concept of the beats phenomena to try to establish how we could calculate vehicle speed using the rumple strips. And it worked just as well. So it's a very accurate method that doesn't require sophisticated equipment other than a recording medium. Now, in the paper that you have in front of me, which is the paper I'm just describing, has examples of what the impulses look like. You have vertical frequencies extending from 0 up to about 500 hertz, and you can see when they begin and when the first impact happens and then the second impact happens. We also ended up using horn to establish synchronization of the cameras and the microphones, as well as a clapper board. So what I mean by that is, in order to synchronize the audio between the different types of cameras that we were using, I decided that we should use the clapper board, which everyone has probably seen in movies where they say lights, camera, action, and they slap this board. That in itself created an audio cue, which allowed us to synchronize the data. But then I also ended up using the horn. And then that's when you start realizing that the horn has its own signature and that the clapper board has its own signature. And if that's not even interesting, I want to let you know that the turn signals have their own signature. And then you have acceleration. What I initially thought was supposed to be very simple has now turned into a project that has taken a life of its own because there are so many avenues. I have been contacted by attorneys to determine whether or not their client had their turn signal turned on prior to a collision. And if you look at it in the spectrogram, you have a definitive signature, and you also know when the impact takes place. So now you know how long prior to the collision this turn signal was actually turned on. And that is probably impressive in my opinion, because in the past, you just had to go off of eyewitness testimony or the testimony of the driver. But now you have an actual diagram that you can actually say, yes, that is when it happened.
Right. It's a real more objective method of doing that sort of thing. So when you finally did this and you're like, hey, we can get speed within a reasonable margin of error or whatever. So what questions opened up for you next, and what led you into the next paper? Let me flip on to that one here. So speed determination using audio analysis of dash camera video from passenger vehicle tires frequencies for vehicle accident reconstruction.
So after the first paper was written, I noticed there was a frequency that just kept changing with vehicle speed, except it wasn't a simple calculation of taking the rotational velocity of the passenger vehicle that we were testing. It just wasn't. It wasn't lining up. The frequency was much too high. And I reached out to Tony Cornetto of Momenta, and I told him about this. And he's the one who came to this conclusion. You know what? I bet it's a speed trace of the vehicle. But I explained, but it's not making sense. He said, if it has something to do with it, maybe it has something to do with the tires. Maybe it has something to do with the gearing system. So we started throwing all these ideas out, and I came back and I focused on the tires. And it turns out that the tires actually play a major role, because if you think about it, a tire is like a gear rolling down the roadway. Every time that gear makes contact, the teeth on the gear make contact with the roadway, it makes a sound. So now that made sense, but yet the frequency still wasn't matching up. So I thought it has something to do with the tire blocks, but something's still not making sense. And then when you look at the tire in a more detailed manner, you realize that the tire blocks on the inside of the vehicle versus the outboard are not perfectly in line. They're offset. So now if you have 10, let's say 50 tire blocks on the outer, you have to count the 50 on the inner. So now you're looking at 100 tire blocks, not just 50. And then once I took that into account, the equation matched up with the frequency trace, but it still was off by about a 5 mile per hour difference. So I reached out to Lou Peck, and I showed him my research because I needed him to consider doing research with us on motorcycles, because he happens to be the motorcycle guy. Mm-hmm. And then that's when he recommended, what are the chances that it's not the radius, that it's actually the circumference of the tire? Because if you take into account the radius and the number of tire blocks and the frequency, and you put it into equation, which I wanted to start referring to it as the Vega equation, you can calculate a speed. But when Lou looked at it, he said, what are the chances it has nothing to do with radius? What if it has something to do with circumference? And if you think about it, a loaded tire is no longer round. Right. It's actually deformed slightly. So I went out and got a seamstress tape measure, wrapped it around the tire. And lo and behold, when you take into account that minor difference, it actually made the equation that much more accurate. So now this equation, if you know the circumference of the tire, the number of tire blocks, and the frequency pulled from the spectrogram, you have speed. And you don't have just 5 seconds as event data recorders have. You have however long you're recording. But there was a limitation to this. I noticed that it was only working on concrete surfaces. And that's when we realized it has to do with not only the tire characteristics, but also the roadway surface. So we made great advancements. And that's when I realized we have to do testing in commercial vehicle tires to see if, in fact, we have the same results. And I will definitely go into that. But in order to finish up this paper, I had Tony Cornetto out on the East Coast take measurements with his vehicle. And we ended up getting results, but we got slightly different results because Tony's data actually had harmonics, which means you had the frequency of the rolling wheels, but you had them in multiples stacked above. And after many, many months, I finally realized, what are the chances that this has something to do with Tony's tires that may be worn out? So I reached out to him and asked him, are your tires out of rounds? And he said, yes. And then I asked, does your vehicle start to vibrate at a specific frequency? It's like a specific speed. And he said, yes. And that's when I realized that audio analysis was very useful in helping us to understand the characteristics, not only of the speed, but also of the tires in question that are actually being used. So then I asked the guys out in California to take measurements, and we couldn't find a single measurement that was recorded in California's concrete roadway. And then we realized California has shredded tires that are grounded into the concrete mixtures for the purposes of dampening the sound.
Right.
But that isn't the case across all of California, because when I was out there giving a presentation for cars, I took sound measurements and I got the frequency trace that I needed. So I'm under the impression that maybe it has to be concentrated to a certain area in California where shredded tires are used to dampen the sound.
So what is the minimum information that you need in order to calculate the speed? So you need to know the vehicle, you need to know the model tire, what do you need to know?
No, interestingly enough, if you look at the equation, and this is something I was mentioning when I was presenting this method out in California for cars in Northern and Southern California, I had mentioned, does it matter what year and make and model of the vehicle? And I got silence. And I said, let's look at the equation. Where in the equation does it tell you to enter the year, make, and model of the vehicle? It doesn't. The only thing that equation is asking you is the frequency, the circumference, and the number of tire blocks for that tire. That's all you need. So if that vehicle is no longer available, I would highly suggest that you obtain exemplar tires and place them on a vehicle and test it over that roadway. Now, I'm sure that some attorney is going to say, well, it's not the same vehicle. Well, then in that case, get one that has that same make and model. But it's not going to make a difference, because it doesn't matter what type of vehicle is being used. It only matters what type of tire.
It's the tire. It's the rotation of the tire and the contact to the road. That makes sense. So do you know how, so for example, if you have let's say a semi-worn tire versus a brand new tire, and they're sort of moving at the same speed, is there a lot of sensitivity to error?
Well, if you look at the paper, the second paper, you'll notice that Justin had actually zoomed into a section of the frequency, and you can actually see that if you chose the upper band of the frequency trace versus the lower band of the frequency trace, you're looking at, if I recall, a spread of 1.5. Would you mind pulling that up?
Do you remember where that is? Is it further down here? Let me see. You might have to help me out here.
Sure. Oh, it's not on the screen right now.
Oh, it's not. Let me bring that up. Sorry about that. Cool Relief Interchange Roadway. Let me see if I got it here.
Go down more. A little more.
Now we're into the
then
discussion.
it must be further up.
Okay, let me go back up. I saw something here. Let me see if I can bring it up. I saw this thing.
Oh, there we go. There we go. Figure 11. Figure 11 shows that the frequency trace, when you zoom in up to it, you can either choose the upper or the lower portion, and it's a spread between a 1.6 mile per hour. So when we were doing our analysis, we were selecting the midpoint, the median of that frequency trace. Now, we noticed that the thickness of that trace actually increases and decreases based on tires being out around. So I imagine that not every single tire is rotating at the same frequency or has the same roundness, and as a result of that frequency trace actually increases as a result of anomalies on the tire itself. And that's something we noticed with Tony's testing out on the East Coast. And I was glad that we had that, because we ended up learning far more than we initially thought. So now we know how to address when we see various frequency traces. We can come to the conclusion that those tires must be out around.
Yeah. Hey, you sent me a few samples of audio, and I don't know if this is a good time to play some of these, but
sure.
You had some of the vehicle stuff. You had like this motorcycle collision. You got the tractor. You got this. You said one that came from. Is it? I don't know if it's Mustang or something like that, and a doorbell. We also have the firearm one. I think we'll hold off on that one until just a little bit later. But do any of these like?
Yes. For example, I found another way of actually calculating speed is if you know the frequency of the skidding tire, and that's where I believe that's where we first met. I found you in the hallway, and I was like, "Hi, I'm Henry Vega, and I want to introduce myself." And I was there for Rex. I was part of the pedestrian crash team where a pedestrian was being impacted by a Mustang. So I ended up recording with my mobile phone the collision itself, and then I went back and I actually looked at the audio and realized that the skidding tires produce a very definitive frequency. And when you take into account the timing of the frequency and what kind of frequency, you can actually calculate what the speed is at various points. So this is another method different than the method that we have published. And
let me play this here just a couple of times so people can hear this. And fortunately, it's audio, so if you're listening to the podcast, this will work for you. So let's play this.
So in that audio clip, we have a Mustang that's being accelerated, and then it's impacting a pedestrian, a rescue Randy that's being held together over a wood structure. And then after impact, the driver applies the brakes of the vehicle, and that's where you have the skidding. And we know where the vehicle came to rest, along with the pedestrian. And that in itself, you can actually calculate the speed using the traditional methods. But if you have the audio, you know exactly when the impact took place, which is time zero. And then you know when the skidding takes, how long it takes or how long after. And you can actually work your way back and you can actually calculate the speed. This method is something I haven't seen using the audio portion for the purposes of reconstruction using the skidding.
What about the motorcycle collision? I'll play that, but maybe you can preface this with a description of what's happening there. In
that case, there was a surveillance camera that was angled and noticed two motorcycles going by. The first motorcycle was traveling the speed limit. The second motorcycle was obviously not traveling the speed limit because it was moving faster. But if you look at the audio track, you can definitely compare the signatures and you can say one is obviously traveling faster than the other. But other than that, we were using the Doppler effect to calculate speed. Not only that, if you know the distance of the skid mark and you know the timing of the skid mark and you know where the frequency, what frequency to actually look for, I was able to calculate the speed, which was much higher than was initially calculated because the individuals who calculated the speed for the motorcycle in that case were limited by the limitations of the equations using stiffnesses, which they were really limited because it was a police vehicle that had a cage in it, which therefore increased the stiffness, and that type of vehicle was not tested. So therefore, they knew their limitations, and they calculated to about 71 miles an hour. But if you take into account the Doppler effect and the skidding, the timing of the skidding, the speed was much higher than 71 miles an hour. Okay, let me play this here. I'm going to boost the volume a bit, and hopefully this will come through well. And again. So it's that little sound that we're hearing, yeah? Yes, there were two sounds. So the first one is the first vehicle is traveling speed limit. The second one is not. Okay, yeah, I hear it. Cool. So, you've got another one here. It says doorbell. So what's the doorbell one? That one is a surveillance video of a nighttime collision of a heavy vehicle and a passenger vehicle. This is classic because this is one of the main reasons I wanted to write the first paper, which was if you have video, you can and if you have ideal conditions, you can calculate the speed. But what if you don't have a line of sight of the collision in question, but all you have is sound? And this is exactly what we have here. So what we have is a tractor vehicle making a right-hand turn, and then you have a passenger vehicle approaching and rear impacting the heavy vehicle. When you look at the video, there's nothing that you can actually determine based on the limitations. But if you look at the audio, you know when the skidding took place, when the impact took place. But also, this is even far more interesting. You find the second impact, the secondary impact post collision. So now you can actually calculate the post collision speed if you know the distance between those two objects. And I thought it was fascinating because most people would have just said, we can't see the collision. And that isn't true. And people internationally have reached out to me and told me, I have a case where we don't have the collision recorded, but the audio, and I've read your paper, and I was wondering if maybe you could take some time and explain to me whether or not this is an ideal case.
Okay, let's play this one. Here we go.
So the first impact was much louder in intensity, and then you have the second impact, which was secondary, and it was lower in intensity. So once again, if you have those details, you can actually determine post-collision travel. And actually, when I was working on this whole audio aspect, Tony Cornetto once again reached out to me and said, I have a case that I need your help on where we have a motorcycle that impacted a passenger vehicle. And I told him, this is when skidding started. This is the speed, and there's a secondary impact. I don't know what it is. And that's when he told me, yes, there is. This is the speed I calculated. This is what the secondary impact is. And you could tell gear shifting on the motorcycle and downshifting. And once again, every time we look into an audio case, there's more information that we normally would have just overlooked. And that's when I ended up meeting Alan Essay when I was at Congress for the SAE presentation, Rex. He had told me, we haven't been listening to the evidence, and he couldn't be further from the truth because have we? No, we've been looking at the evidence, but have we been looking at the evidence? And the answer is no, we haven't.
Right. Really good point. Looking and listening are two different things. So let me switch over or ask you about firearms. Now let's move over into this particular area because sure. We did a little bit of work there, and I think we've got a sample of one of the videos that we recorded. I think that's what one of the things you gave me here. So if you want to, maybe let's talk about. I mean, you started with at the beginning of the talk about this case you had with shooting and firearms, and then so there's things that you can determine, like how many shots are fired and things like that. But there's actually more that's sitting there. And I think that's one of the things we found. So help me out here. What kinds of things can we determine from the audio, from a body camera or a bystander phone or something like that?
Well, sound is highly dependent on where the sound originates from in the environment that it's in. And if you have to say that a couple times to truly understand. So if you create a sound, that sound is going to be different where it's actually produced, whether it's a hallway, whether it's an open room, whether it's a room with carpeting, or a room without carpeting. And this is something that I was pursuing when we ended up doing research together. I ended up taking the body camera footage from your testing that you conducted up in Canada, and I was able to find a detail that I had not considered before. For example, a discharge. Granted, we could find out different calibers if we end up doing some pretty complex mathematics on it instead of just looking at the spectrogram. It's a whole different topic in itself. So it's not just about looking at the spectrum. It was actually processing the information in a completely different manner. But aside from that, I noticed that the casings falling on the ground produced a very distinctive frequency signature. And I realized that they even had a frequency signature unique in itself, even though you were comparing two of the same caliber. So if you had a caliber of one manufacturer, that same caliber produced a very distinct frequency if it was a different manufacturer of the same caliber. And I thought, this is an amazing aspect because I can imagine that coming up in the future. The casing falling on ground would create the frequency associated with that caliber, but not only that, but also with the manufacturer in question.
Yeah. Let me preface this. So the testing that we did, so I ran the testing up here and then I sent you all the footage. So just so people understand, we have a shooter, and that shooter is surrounded by a grid of cameras. So we were using some Axon Body 3 cameras. I believe we had 5 of them, and then we had a couple of GoPros as well. We put some GoPros out there in sort of different arrangements at different distances from the shooter. So let me play the fired shot. And again, I'm going to crank this up, so be careful of what you're listening. Hopefully, it doesn't blow people's ears off. So let's play this shot first. Okay, so that's the fired shot. And we ran different firearms, like with different calibers, and then we ran the same firearm with different ammunition. Yeah. So we tried a couple of different things. So that was the shot. Let me play it one more time. Okay, and then what we're going to do is, so what did you do to isolate for the cartridge case? Because it may be a little hard to hear it. It's there in the background, but what did you do to isolate for this?
So then I identified the gunshot, which is denoted in a sharp increase in frequencies, which is known as the impulse. And then I isolated the frequencies that had a very distinct bouncing action. And I played that, and that's when we ended up isolating just the casing strapping, which I guess you will play next.
Yes, let's play this. Yeah, so I mean, and this makes a lot of sense. Like if you think about what the example that I used was, the cartridge case is like a little organ pipe. It's a little pipe, and so. Yes. It's going to have a sort of a frequency that it's going to vibrate at or whatever. And, if you're looking at a 45 caliber versus a 22 or something like that, then they naturally will have just different frequencies that they're going to resonate at. So I think that's really interesting. So, would you be able, for example, to tell the difference between the cartridge cases of two different shooters with different ammunition, let's say?
Yes. Under ideal situations, like let's say we actually had a ground that actually would allow the ringing of the casing making contact, I can foresee the next stage in our research. I would recommend dropping 2 different casing. And I'm starting to realize that we don't even need to discharge a firearm in the area. We just simply have to just flip a casing or place a spent cartridge in a firearm and erect the slide, and that would eject it. By doing so, I believe we can actually pinpoint exactly which one fell first. And because we're dealing with audio, and audio is amazingly accurate in terms of we're dealing in hundreds, thousands of a second. So we can come very close to delineate between which casing fell first versus which one did not.
Yeah, that's pretty amazing. I love it, and I think there's a lot of opportunities there. So let's talk about what's next, Henry. So like you got out. You were at the ITI conference in England like last week. So maybe talk about that and what you were doing there last week, and then I'd like to ask you also like, what are your next moves? Like what is the next priority for you in terms of research or advancements in these areas?
Well, when I was out in the UK, it's because I met Mark Crouch and Stephen Cash, and they were interested in knowing how this whole audio could work in collision reconstruction. And once I explained to them, they said, well, we're going to be doing testing out in the UK. You're welcome to come. And I'm glad that I was given the opportunity, because I was able to place a GoPro as well as a Rode wireless microphone inside the passenger compartment of the vehicle that was being tested. And then I also had an exterior GoPro and Rode microphone at a stationary location. Both systems had two-way radios. So if you think about it, if I have a third radio and I click the radio to say test 1, click, that clicking is a synchronization for the cameras on the exterior and the interior. And when I did that, I was able to synchronize the audios of those 4 different channels. And then I evaluated it and realized that there was a speed trace too, that there was data there, and there's data that I never even considered before. So that information is going to be compiled, and it's going to be processed and shared with the UK community for our agreement, because I was given the opportunity to go out there, and it's only fair that I process this and share it with the community out there. As a result, I met individuals in law enforcement out in the UK who are interested in learning this audio method. And I can see why, because if you don't have video, but you have audio, you certainly have the opportunity to make calculations. In those cases, when we were out doing crash testing, pedestrian crash test was tested, poles tested, as well as multi-vehicle collisions. And the amount of information you can see, it is amazing. And it almost looks like artwork, in my opinion. I think I might even consider actually printing out something and hanging it on my wall, because I think this is an avenue that has opened up a whole new horizon. So with that, that's what I'm doing. That's what I did about 2 weeks ago. So to answer your question, what other aspects am I going into next? We ended up doing testing with commercial vehicle tires. And it turns out that the amount of information with commercial vehicle tires being produced in audio far exceeds passenger vehicles. In other words, commercial tires have a speed trace regardless of the roadway. Whether it's asphalt, whether it's concrete, it's producing a signature, whereas passenger vehicle tires being softer, I imagine, don't have the same effect. And it was Jeff Suey who pointed that out to me, because I told him, I'm not understanding why we're having signatures in commercial vehicle tires where we're not having in passengers. And his response was, they're stiffer. And I thought, you're right. It's like, I can't see the forest because of the trees. It was blatantly obvious, but I needed someone to point this out to me. I guess I got tunnel vision.
Yeah, that's super interesting. So that's something you're going to be looking at too then. Okay. Well, I know that I'm going to be bugging you about firearms again.
Yes, I am very, very interested in doing more research. Oh, but there's one more research I forgot to mention. We're doing research with Lupec where we're taking motorcycle tire data and try to determine speed that way. I think there is an avenue that I was not expecting, and that's something I need to sit down and speak with Lupec about, because I think there's an avenue that needs to be explored that I did not see coming. But other than that, I am also looking forward to doing firearms testing with you again. We've talked about our next phase. I think if you recall, I think you were referring to them as phases. And I like that process, that we should test it out and then have others see if the results could be replicated.
Yeah,
I think it would be interesting to see if we can determine different firearms discharged at the same time, because that's the kind of cases I worked out in the past, and because it's more realistic. Usually, when you have a shootout, you have more than one firearm being discharged.
Yeah. Hey, Henry, if somebody wants to get a hold of you or they have some questions or whatever, I've got the company website up here, but I'm guessing there's a contact window there. And I think you're on there. There's like an about page or something that shows your information, right? So the jsforensics.com, and I guess people can go there. And you're also on LinkedIn, right? You're on social media too.
Yes, I am.
Okay, great. Look, thanks so much for your time and for everything. I think it's just an amazing opportunity that you have here. You've opened up a whole bunch of doors on this whole audio thing, and just like the little that I've seen with the firearms and some of the papers you're doing, it just sounds really just promising, like giving people another window, another opportunity, like to do different types of analysis. It's like a secondary way to validate calculations and things. So great job. I love what you're doing, and keep up the great work.
Thank you. Thank you for having me present this. Thank you.
All right. Hey, hang back. I'll come back and chat with you in just a second. All right, folks, that's it. Another episode of Forensics Talks. Really interesting what's going on there in the whole audio analysis world. And, sometimes with audio analysis, people are thinking about making identifications or, is it this speaker or that speaker? But this is a whole other realm here. And so, hey, thanks to Henry again, and I really appreciate his time. So thanks to all of you for listening. Happy Thursday. This is going to be aired on a Thursday, and we'll see you on the next one. Take care, everyone. Bye-bye.